Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual landscape of post-war theoretical physics presented a curious paradox. The principles of quantum mechanics and special relativity, the two great pillars of early 20th century thought, have been successfully amalgamated to create quantum electrodynamics, the theory of light and matter. Yet, this union was a troubled one, plagued by persistent and profound mathematical pathologies. When physicists attempted to calculate physical quantities like the self-energy of an electron, their equations yielded infinite results, a clear signal of a deep conceptual failing. The community wrestled with these divergences using complex and often ad hoc subtraction techniques, existing in a state of what one might call pragmatic despair. Into this environment of sophisticated mathematical machinery and lingering foundational anxiety, Richard Feynman introduced his 1948 paper, Space-Time Approach to Quantum Electrodynamics. This document was a bolt from the blue, offering a wholesale reimagining of the very grammar of quantum interactions. Its purpose was audacious: to replace the arcane and abstract operator formalism of the canonical theory with a viscerally intuitive picture rooted in space-time trajectories and direct particle-to-particle communication. This essay provides a critical evaluation of the internal claims, mechanisms, and arguments presented within this landmark work, proceeding section by section to analyze the construction of Feynman's revolutionary worldview and assess the coherence of its foundational propositions. Section 1, Redefining the Foundations, draw a space-time view. The paper's introductory passages articulate a profound dissatisfaction with the prevailing Hamiltonian method. Feynman's opening claim is that the standard formulation, which singles out time as a special parameter, obscures the manifest relativistic covariance that a true physical theory ought to possess. The Hamiltonian approach requires a step-by-step evolution of a system state vector through infinitesimal time intervals, a procedure ill-suited to the block universe perspective of relativity, where space and time are interwoven. Feynman proposes to supplant this with a Lagrangian approach. The core argument here is that the classical principle of least action, which determines a particle's trajectory by minimizing a quantity called the action integral, holds the key to a more natural quantum theory. His claim is that the action, a scalar quantity defined over a whole segment of a trajectory, is inherently relativistic and offers a global, space-time perspective. The work immediately sets out to build a quantum mechanics based on this principle, aiming for a theory where the state of a system is described by an amplitude for it to get from one spacetime point to another, dispensing entirely with the machinery of field operators and state vectors evolving in time. The evaluation of this initial claim rests on its promise. Feynman is essentially arguing for a shift in the fundamental question of physics, from how does a system evolve from one moment to the next, to what is the total amplitude for a particle to travel between 2 points in spacetime. This reframing is the conceptual bedrock upon which the entire edifice of the paper is constructed. Its validity is to be judged by the coherence and calculational power of the structure that far. Section 2, The action principle and the sum over histories. Having established his philosophical preference for the Lagrangian, Feynman presents his first major physical postulate, a radical reinterpretation of quantum probability. He claims that the total amplitude for a particle to propagate from a spacetime point 1 to a spacetime point 2 is found by summing the contributions of every conceivable path connecting them. The contribution of each individual path is a complex number of unit magnitude, a phase. Specifically, this phase is given by the expression e to the power of the imaginary unit I multiplied by the classical action for that path, all divided by the reduced Planck constant. This is the celebrated sum over histories or path integral formulation. To validate this audacious claim, Feynman demonstrates that for a non-relativistic free particle, this prescription precisely reproduces the familiar results of standard quantum mechanics. He shows how this summation over an infinity of trajectories when analyzed, yields the Schrödinger equation for the evolution of the wave function. This demonstration is a crucial piece of internal evidence. By recovering a known and verified equation from his new, seemingly bizarre starting point, he establishes a bridge of logical consistency. The evaluation of this section's claim is therefore twofold. First, the postulate itself is an act of supreme physical intuition, replacing the deterministic evolution of a wave function with a democratic summation over all possibilities. Second, its justification is purely operational. It works. The argument's power lies in its ability to subsume the old formalism within the new one, presenting his approach as a more fundamental and encompassing viewpoint from which standard quantum mechanics emerges. As a specific consequence, Section 3 interaction as mediated exchange. The next stage of Feynman's argument involves the introduction of electromagnetic interactions. This is where the paper's departure from canonical methods becomes most pronounced. In the standard formalism, interactions arise from a charged particle coupling to a quantized electromagnetic field, complex system of operators that create and annihilate photons. Feynman claims that this entire field apparatus can be eliminated from the fundamental equations. He proposes a mechanism of direct interaction between charges, an action at a distance theory reminiscent of classical electrodynamics, yet with a crucial quantum modification. He achieves this through a masterful technical maneuver. The total action for the system is written as the sum of the actions for the free particles plus an interaction term. This interaction term involves the particle currents coupling to the field. Feynman then treats the field itself as a collection of harmonic oscillators and, in a key step, performs a functional integration over all possible field configurations. The result of this integration is a new, effective action that involves only the particle variables. The field has vanished, and in its place is a term describing a direct interaction between two different currents at two different spacetime points. This interaction is mediated by a function, the propagator, which he shows as a delta function of the squared spacetime interval between the 2 points. This claim is revolutionary. It asserts that the entire concept of an independent, quantized field is a calculational convenience, a piece of scaffolding that can be removed to reveal the true underlying structure, particles acting on one another across spacetime by exchanging a quantum of interaction. The evaluation of this section must recognize its conceptual elegance. The Baroque complexity of the quantized field is replaced by a single, clean rule. The evidence provided is the mathematical derivation itself, a tour de force that transforms the physical picture of reality. Section 4. The positron as a world-lying reversal with the machinery for particle interaction established. Feynman confronts the deepest puzzles of relativistic quantum theory, self-interaction, and the existence of antimatter. An electron interacting with the field it generates leads to the infamous infinite self-energy. To handle this, Feynman introduces his most startling and iconic claim: a positron is mathematically and physically equivalent to an electron that is propagating backward in time. This is a profound reinterpretation of the solutions to the Dirac equation, where Dirac had postulated a sea of negative energy electrons, with holes in the sea behaving as positrons. Feynman offers a dynamic, spacetime picture. An electron can travel from point A to point B, emit a photon, scatter backward in time to point C, and then absorb another photon to continue forward in time to point D. From the perspective of an observer moving forward in time, this sequence appears as an electron travelling from A to B, then the spontaneous creation of an electron-positron pair at C, with the new electron travelling to D and the positron annihilating with the original electron at B. The evaluation of this claim centers on its extraordinary problem-solving power. This single postulate unifies a host of disparate phenomena: electron scattering, positron scattering, pair annihilation, and pair creation become different aspects of the same fundamental process. Simply viewed from different spacetime perspectives, it provides a natural language for describing processes involving loops, where a particle interacts with itself. The evidence for this claim is its logical economy and its ability to construct a consistent calculational framework for processes that were previously cumbersome to describe. It transforms a mathematical quirk of the Dirac equation into a powerful and intuitive physical principle, a signature move of Feynman's cognitive style. Section 5. The synthesis of relativistic rules and renormalization. In the paper's climactic sections, Feynman synthesizes these conceptual elements into a concrete set of calculational rules for quantum electrodynamics. The claim is that any observable process, such as the scattering of two electrons, can be computed by drawing all the possible spacetime diagrams representing the interaction and then translating each diagram into a mathematical expression using a simple set of rules. He provides the explicit mathematical forms for the key ingredients: the propagator for an electron or positron travelling backward in time, a propagator for a photon the mediator of the interaction, and a vertex factor for the point where an electron emits or absorbs a photon. The amplitude for the entire process is the sum of the amplitudes for each corresponding diagram. This is the birth of the Feynman diagrams and their associated rules, a system that would democratize QED calculations. Critically, Feynman directly addresses the problem of infinities. He acknowledges that diagrams with closed loops, representing an electron self-interaction, lead to divergent integrals. His proposed solution within the paper is a regularization scheme. He suggests modifying the photon propagator at very short distances, effectively introducing a cutoff parameter, and then arguing that the final physical results should be independent of this cutoff as it is taken to infinity. The evaluation of this section is nuanced. The claim that his rules provide a complete calculational framework was correct and transformative. The simplicity and visual power of the diagrams were a pedagogical and practical breakthrough. However, his treatment of renormalization in this paper is more of a proposal and a complete, rigorous theory. He provides the means to get finite answers for physical processes, but the full mathematical justification for while his procedure is valid and systematically applicable to all orders was still to come. The work of Freeman Dyson, who shortly thereafter proved the formal equivalence of Feynman's intuitive method with the more rigorous but forbiddingly complex operator formalisms of Julian Schwinger and Shinichiro Tominaga, provided the ultimate external validation for Feynman's claims. Dyson's proof cemented the legitimacy of Feynman's rules, showing that his intuitive physical picture was built on a solid mathematical foundation. Section 6. The philosophical and pedagogical implications. In his concluding discussion, Feynman reflects on the nature and advantages of his spacetime approach. He claims his formulation offers a greater degree of physical intuition than the abstract Hilbert space methods. It allows a physicist to visualize processes as they unfold in space and time, to picture particles exploring all available paths, exchanging quanta of force. This claim about intuitiveness is itself open to evaluation. For many physicists and students who followed, the diagrams and the underlying path integral concept did indeed provide a powerful and clarifying mental model. The idea of a particle sniffing out all possible routes as a compelling physical narrative. There is a certain intellectual irony that this intuitive picture is built upon such non-classical and mind-bending concepts, summing over an infinity of paths and allowing particles to travel backward in time. Feynman also argues that his formalism is more flexible and potentially more generalizable to other forces, such as the mysterious nuclear forces. He saw the action principle and the direct interaction picture as fundamental building blocks that might transcend the specific context of electrodynamics. This claim proved to be prescient as path integral formulations became a cornerstone of modern quantum field theory, particle physics, and even condensed matter physics and gravitation. The evaluation of his concluding remarks confirms the lasting philosophical impact of the work. It altered not just how physicists calculated, but how they thought about the fundamental nature of reality. Conclusion: Feynman's 1948 space-time approach to quantum electrodynamics is a document of profound intellectual synthesis and startling originality. A critical section-by-session evaluation reveals a carefully constructed argument that begins with a philosophical reappraisal of physical law and culminates in a powerful and practical calculational tool. Its central claims, from the foundational Summa history postulate to the revolutionary interpretation of the positron, were substantiated within the paper through a combination of logical derivation, recovery of known results, and the sheer explanatory power of the resulting framework. While the paper's treatment of renormalization was programmatic, it provided the essential machinery that, when later proven rigorously equivalent to other methods, completed the edifice of modern QED. The work's genius lies in its dual nature. It is simultaneously a pragmatic manual for performing complex calculations and a deep meditation on the underlying structure of the quantum world by replacing the abstract evolution of state vectors with the tangible imagery of particles traversing all spacetime paths and interacting via direct exchange. Feynman provided a new language for physics. This language, built on the claims articulated in these pages, possessed a unique combination of intuitive appeal and quantitative rigor, and its grammar continues to shape the dialogue of theoretical physics to this day.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.